Guys, today we are going to look at this problem. It's published by Dash, right? So I'm very glad that you bring this up because it's a very interesting problem and it helps us understand a very important algorithm, right? So let me introduce the problem first. So here is a example. It has the first three numbers are um, the number of nodes in the graph, and the second is uh, the number of edges in the graph, and the third one is the start node index, right? So what is the graph? It's here. So we have 9 nodes, right? And the edges between the nodes are 1, 2. So here, 1 to 2 is a one-way path, right? 1 to 2. And 1 to 3, 1 to 3. 2 to 3, 2 to 3. So that's it. You get the idea. So that is the graph we have. 4, the node 4 doesn't connect to any node, right? So it's an individual one. And the starting node is number 1, right? The first node is a starting node. And the output here is that how many edges we need to add to this graph so that we can reach any node in this graph from the starting node, right? So the output here is 3, right? So after we add 3 edges, we can reach any node from node 1, right? So let's first find out which node we cannot reach from node number 1 in the original graph, right? So we can reach node 8, right? Through this edge, and we can reach node 5 through this edge, and node 6 through this two edge, right? And we can reach node 2, right? And node 3, right? And these 3 nodes we cannot reach. So all we need to do is to add 3 edge to the graph so that we can reach any node from the first node, right? So how do we find out the minimum number of edges we need to add to this graph? We need to introduce an algorithm here whose name is Tyent, right? The algorithm's name is Tyent Algorithm, right? So this algorithm is to find the strongly connected component, SCC, right? Strongly connected component in this graph. So what is SCC, strongly connected graph component, I mean? So here is a strongly connected component, right? Because you can reach any node from any node. For example, you can reach 1 and 5 from 6, right? And you can reach 6 and 5 through 1, and you can reach 1 and 6 through 5. So that is a strongly connected component. So in this kind of component, you can reach any node from any node, right? Is there any SCC we can find in this graph? So let's see. No, not anymore, right? This is the only one. And the other SCCs are the individual single nodes, right? These are SCC itself, right? So let's give another example here. So this component is a SCC. Why? Because you can reach any node through any node, right? So this is an example of SCC as well. So let's say if we already find several SCC, let's say we use a number to index the SCC. Let's say this guy is SCC1, right? And this guy is SCC2. This guy is SCC3. This guy is SCC4. I mean, this guy is SCC4. This guy is SCC5. This guy is 6. This guy is 7, right? So all of the numbers are SCC now, right? And we have 7 SCC in this graph. So how can we find how many edges we need to add into the graph? Let's count how many SCC does not have in degree, right? So in degree means that there is an edge from one SCC to another SCC. This guy is in degree of SCC1, right? From SCC5, right? So how many of them does not have does not have in degree? So let's iterate each SCC, right? For this one, because this SCC is SCC, it is the starting point. This SCC contains the starting point, node 1, right? So it automatically has in degree. And let's iterate to the SCC2. So this guy also has in degree. This guy also has in degree. And where is the 4? This guy does not have in degree. So that's one SCC we need to add edge to, right? We need to add an edge to this SCC, right? Otherwise, this guy cannot be connected, cannot be reached by the first node, right? And what about the 5? SCC5 is here. So no in degree for this guy. So we add a road to this SCC as well. And how about the 6? 6 has a SCC, right? Has 2 in degree, right? This one and this one. So this guy is good. What about SCC7? This guy does not have in degree. So we need to add the last road to this SCC, right? So in total, we need to add 1, 2, 3, roads to those SCC does not have a in degree. So why can we do this? Because this guy is SCC, so that we can collapse these three nodes into one, right? Because these three nodes can reach each other anyway, so we can just collapse it into one node. And um, this SCC contains the starting node, so it automatically has a in degree. And what about this guy? Because this SCC has in degree, so we don't need to add another one here, right? Because if we add another one, it will be a waste, right? So let's say if we already find out all of the SCC in this graph, we can solve this problem very easily by just counting the number of SCC that doesn't have a in degree, right? So how to calculate the SCC? We are going to use Tarjan, right? Very important algorithm. So the input of Tyent is the graph, right? You have several nodes and you have several edges, right? And the output is a array that each node in this array is a SCC index of that node. For example, for this graph, the node 1's SCC index is 1, and the node 5 index, node 5's SCC index is also 1, right? And the same as node 6 index, SCC index is also 1, right? So how do we calculate the output here? So we are going to use deep first search and also use a stack, right? So the stack here is first in, last out, right? So how do we do it? Let's say we have a stack here, right? And we are going to deep first search from the first node, right? And we push this node into the stack, right? And we move on. Deep first search, or its out degrees. So we come to node 5. So we haven't visited node 5 yet. So we push this guy into the stack, right? And before we moving on to calculate the Tyent algorithm, we are going to have two features for each node. The first feature for the node is, let's write it down here. The first one is number, right? And the second one is low link. Let's just say call it low, right? We have two features for each node. So the first feature is the is the number where we visit this node. For example, the first node we are visiting is node 1, right? So its number is 1. The second node we are visiting is node 5. So node 5's number is 2. And the third node we are visiting is 6. So node 6's number is 3, right? And what is the low here? Low means the lowest number the node can reach, right? For example, for now, the lowest number node 1 can reach is itself. So we set it as 1. And for the node 5, the lowest node it can reach is 2, right? Number it can reach is 2. And the for node 6, the lowest number it can reach is 3. And we keep doing the deep first search. Now we encounter 1 here. So we visited this guy before. So we update the low here, right? Because it already has a number. So the lowest number node 6 can reach is 1 now, right? So we update the low here. And we backtrack, right? We get back to node 5. And now the lowest number node 5 can reach is also 1 now, right? So we back to here. And then we backtrack. Before that, when we visit node 6, we forgot to put this node into the stack. So we put it in, right? And then backtrack to node 1. For node 1, we keep deep first search. Visit this node 3, right? So the number of node 3 is 4 because it's the fourth number we visit, right? And the lowest number it can reach is also 4. Now we already visited all of node 3's out degree, right? He has no out degree anymore. And let's check if its number equals to the lowest number it can reach, right? 4 equals 4, so that we are going to remove it from the stash and assign the SCC index to this node, right? So because the lowest number it can reach is itself, so itself is a SCC, and its SCC index is 1 because it is the first SCC we found in the graph, right? And then we move on. So the last, the second last out degree of node 1 is here. So we push 2 into the stack, right? And we are here. And then we check its out degree, this one. And this, let me see. And this guy already, we already visited this guy. And this guy is not in the stack, right? So we can be sure this node is not going to be in the same SCC with this node because this node already belongs to other SCC, right? So we don't need to visit this node anymore. So we backtrack, and this node itself is the lowest number it can reach. So this guy itself is also a SCC, right? So this guy is SCC2 here. And we move on. The last out degree of node 1 is here, right? And we because we already find the SCC for this node, so we remove it from the stack, right? And visit this node 8. So we push 8 into the stack, right? And 8 does not have out degree anymore, and the lowest number it can reach itself again. So node 8 is also a SCC, right? It's SCC3, right? So now all of node 1's out degree are visited. So what we do next is to check if node 1's uh, node 1's lowest number it can reach is itself. So we need to, here is the most critical part. We need to make all of the numbers come before the node to the same SCC, right? In this case, we pop up the first guy in the stack, which is 6. So its SCC is 4. And we pop it. And it comes to number 5. So this guy SCC index is also 4. And we pop it out. And finally, we found number 1 here. So itself SCC index is also 4. And we pop it out. And we stop here. So that is the Tyent algorithm. Now we find all the SCC index for these guys, and we are going to run Tyent algorithm on all of those nodes, right? So we move on to node 2. So node 2 already has a SCC index, so we skip it. Also, node 3 already has a SCC index, so skip it until we come to node 4. It doesn't has a SCC, so we run the algorithm. So itself is a SCC. So the SCC index is 5. And in the same way, this guy's SCC is 6. And this guy's SCC is 7. So in total, we got 7 SCC. And how many of them has just one, doesn't have any in degrees? So we count for the first SCC. The first SCC is here, so it has 2 in degree. So the counter is still 0, and we check the second SCC. Its in degree equals to 1, so we check the third. Its in degree is 2, so we check the fourth. It has a start node in the SCC, so we keep moving on. And for SCC5, the integrity is 0, so we increase the counter and move on. The 6 has no integrity for this SCC, so increase the counter. And finally, we come to SCC7, and it has no integrity, so we increase the counter to 3, and we output 3 here. So I guess that's it. I hope I explained the Tyent algorithm well. So if you cannot understand it, you can check out some other tutorials. I will put those tutorials link below the video, all right? So check it out. So with all those being said, we move on to the code, right? So here is the code. The left part is the Tyent algorithm, right? The right part is the main algorithm, right? So this part is where we input all those edges, right? And this part is where we run Tyent algorithm on each of the node. And before we run it, we need to check if it already has a number. Because if it has a number, we have already visited before. We don't need to run it again, right? And here is where we set the number, the initial low, and put it into the stack, right? So this part is we keep tracking if a node is inside the stack, and this part is where we actually push the node into the stack, right? And this guy is keep tracking of um, where are we, right? How many nodes we have visited before, right? And this part is where we visit all of those out degrees. So if we haven't visited before, we keep the deep first search, and we make sure we update the low for each node, right? And if the node is in the stack, we need to update the low with its number, right? This guy here is very important. It's not the neighbor's low value. It's actually the number value, right? And after all of those out degrees are visited, we come to the end to check if the number of itself is equal to the lowest number it can reach. If it is, that means we find another SCC, right? And we are going to pop up all of those nodes in the stack and set them as the same SCC, right? So here is where we set, actually it's here is where we set the SCC for those nodes in the stack. And we need to pop out all of them, right? Until here, pop out all of them, right? So that's all. That's how we calculate the SCC in the graph. After we know all those SCC, now we count the in degree for each SCC, right? So this part is where we iterate all of those paths, right? And we iterate all of those out degrees for each node. And um, add in, make the flag to true if this SCC has a out degree. I mean has a in degree, right? So this flag is has in degree here. And after that we only need to count how many SCC does not have a in degree, right? So the answer here is the counter, and we output the counter here. So one call out is that if the SCC has the starting node in it, then we set its in degree to 1, right? So this is obvious. So I guess that's all. Hope it can help you understand the Tyent algorithm and also solve this problem. So as I said before, if I didn't explain Tyent algorithm well, you can just check out the link. I will post it below my video. All right. So cheers. Bye.